Hi, this is Physics Lab 4 Oscillating Spring. The purpose of this lab is to obtain motion position data from the given spring mass video and compare its experimental model with the computational one made in VPython. Observed is a system in which the mass swings in an arc while oscillating on a spring. The motion of this object was analyzed through Tracker and then used to create a computational model in VPython. Physics concepts involved in this lab include the momentum principle, energy principle, and Hooke's law. The results of this lab concluded that the spring mass system does satisfy the energy principle and that discrepancies between the experimental and computational models were due to the drag force experienced by the mass as it slowed down. The predicted motion of the mass followed a very similar path to the experimental data in Tracker. Next, we'll view the video in Tracker and code samples as well as physics concepts, then the experimental versus computational models, and the discussion question. Position data was found and able to be analyzed using the center of mass tool and the calibration stick set to 0.7 meters. As you can see, the spring oscillates while moving in a somewhat circular motion. The data obtained from the object's movement is then depicted in a sinusoidal graph. The data was then stored in a CSV file so the VPython program could access it. This will allow for comparison between the computational model and the observed data. The system's initial conditions include the ball's mass, which is 0.402 kilograms, and its initial position obtained from the Tracker data. The initial velocity of the ball was 0, and the initial time was set to 0 as well. Physics concepts in the next part of the code include the use of Hooke's law to find the spring constant and displacement of the object. The spring constant was found to be 6.8 kilograms per meter squared, or newtons. This value was then used to find the displacement of the object. The code then instructs VPython to access the CSV file with the observed motion data. The time step is then set to 1/210, and the Earth's gravitational force is 9.8 meters per second squared. Solved for previously using Hooke's law, the spring constant is 6.88, and the displacement is 0.128 meters. L and L hat are then set respectively. The three types of energy located in this system are the potential energy of the spring, the potential energy of gravity, and the kinetic energy. Gravitational potential is mgh, while spring potential is 1/2 kx squared, and kinetic energy is 1/2 mv squared. The while loop is then run for 8.8 seconds, and the initial energies are represented as K, Ug, and Us. The F spring is Hooke's law, and F net is F spring plus F grav. The ball position is updated by the ball.pos equals ball.pos plus ball.v times delta t. Here we will observe the module as it runs. The computational model of the spring's movement is then shown, along with a graph of all of the energy of the system. The blue line represents the change in kinetic energy. The red represents the change in spring potential energy, and the green is the change in gravitational potential energy. The yellow line represents the total energy of the system, which we see as 0. When compared to the experimental data, the computational model comes very close. However, the discrepancies between the two can be accounted for by the drag force slowing down the object as it moves through the air. What does it mean? For your model system, is the energy principle satisfied? We see here that the change in total energy equals the change in kinetic plus the change in potential energy. The only energy involved in our system is the potential of gravity, the potential of the spring, and the kinetic energy. We see in this graph that our change in total energy, represented by the yellow line, stays at 0 the entire time. And this means the energy principle is satisfied. Using the data obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and then discuss. The oscillation period for the x position was 1.5 seconds, whereas the oscillation period for the y position was 1.3. The differences in the periods of oscillation are caused by the different equations used to find both the x and the y period. Thanks for watching.